have new material. This is not an antenna for clickers, this is just a pointer. So today we'll finish the tunnels, and this is an important issue for understanding how the migration to IPv6 will occur. Again, that's a topic that will keep communication systems engineers busy probably for the 20 coming years. So it's important to understand the technical details. We'll also quickly talk about link state routing, which is important but intellectually very simple. Tomorrow we'll have the last clicker test. No lab, so the session will be a bit shorter. After the last clicker test, stay in the room, please. We will have the winners of the Best Research Exercise Award, which this year was on how anonymity works in the internet, the Tor solution to anonymity. And they have done the work for you to understand how Tor works. They did their own private lab, and they will present to you how Tor works. And at the end of the presentation, I will grade the presentation by your answers to the questions that I will ask. So the goal is for you to understand how Tor works, and I will ask a number of questions. And if you have shown that you understood how Tor works, then they will get a good grade. And no lab. And for lab 3 and lab 4, I'm sorry, lab 3 is the bottleneck. Miroslav, who has zillions of things to do, is a bit late with grading lab 3, but that will be done this week. And lab 4 is graded, but is waiting for lab 3 because we have a 5.4 channel. Some quick feedback from the evaluation. Those are the evaluations of the course, which this year are very good. I'm very happy, and thank you for everyone to be here. And thank you also to all the teaching assistants. There's a lot of hard work and a lot of time-consuming work. You had a feeling of that because you said it's too long, but you can imagine for the teaching assistants, it's also a problem. Over the years, we moved the lab from Internet Engineering Workshop in INF 019, where we still have all the hardware, to a virtual environment. Last year, it went very smoothly. So we hope this year it went smoothly again. It did for most people, but we had a few surprises with GNS3. In particular, those of you who picked the latest version of GNS3 have had a lot of problems, so we have to stick to the beta version. We hope to solve those stability problems, be able to test them next year, but that is an uncertainty. That is the price to pay. We allow each of us to run in their own environments. Some of you have Windows 8, 8.0, 8.1, Macintosh, Mavericks, Yosemite, Linux this, Linux that. We try hard to make this available under all platforms that we know, but it's sometimes we have surprises. And sometimes we have bad luck. I think this year we had bad luck with GNS3. We'll try to fix some of the things that can be fixed. Something easy to fix is the schedule conflict with the security course. Many of you take the 2 courses, so it was probably not so many in the past years. There's an NP hard scheduling problem at EPFL with the rooms, the options, everything in the master. And usually it's based on artificial intelligence method where we speak to Sylviane Dalmas and say to her, be sure those 2 things don't enter in conflict. And I think we were not on her radar screen. So I'll make sure it is for next year. Doesn't help your problem this year, but hopefully it will next year. The configuration work, we have tried to reduce it. It has been reduced a lot. We give files with all cooked configuration. We'll try to improve a bit for next year. And we'll try to smooth some of the labs. Perhaps lab 2 was a bit too long. Let's see. On the positive side, the videos of lectures which were practically done for all lectures. We had 1 or 2 technical problems. By the way, I'd like to thank Sergio for being here a cameraman and audio recorder for every lecture. And the post-processing also. So many of you said it's useful, particularly if you have the conflict with the other course, so we'll continue to do it. We'll try to do more in the form of going to a MOOC, but that's requires more time. About the clicker tests, I think most of you say that it's good in the sense it pushes it forces you to work during the semester. As an anecdote, I mean, in past years we didn't do it. 5 or 6 years ago we didn't do it, and the failure rate at the exam was much larger. So I think it has a very positive effect. Now it's a bit stressful, I admit, because it's real time, and once you realize you gave the wrong answer and the next question comes, it's too late. One solution would be to do a paper test instead of clicker. It's less high-tech, but it's perhaps more relaxing, and that would allow to give what some of you have asked, like having a joker question, for example, having perhaps 12 questions, and you're allowed to not answer 2 of the 12, for example, to reduce the stress a bit. We'll see how practically it's doable. It is practically doable, but whether we have enough resources to do it, we'll think about it and see for next year. About the amount of work for the electrical engineering students, it's far too much. For the computer science students, it's too much, and it's okay for the communication systems students. I would expect the other way around. I think most of the work comes from the practical time wasted with software issues. So I would assume computer science students are more resistant to that. They consider business as usual, but perhaps not. Perhaps I'm wrong. Voilà. Is there anything else somebody would like to add? Or then if not, let's continue. Things are not finished. So we dive into the topic again of 6-to-4. 6-to-4 is a solution for like-to-like interworking, which is typically this one. In this one, important to realize is there are 2 IPv6 clouds, but they're not symmetrical. This is what we can call the IPv6 internet. And the concept in all interworking and like-to-like solutions is that there is one IPv6 internet. And then there might be IPv6 clouds that are not connected to that, and we need a mechanism to interconnect them. But it's not symmetric. This is, if you want, an island that wants to get to the mainland, not the other way around. And there is a single IPv6 internet that will not use tunnels or whatever for its connectivity. So this is what we say the early adopter problem. That's the problem you have today if by bad luck at home you have only IPv6 equipment, which is unlikely to happen here, but might happen if you're in a place of the world where you receive only IPv6 service. And then we have seen that the very simple solution is to use IPv4 as very much like IP normally uses the MAC layer. So, and it's called tunneling. We put IPv6 packets in IPv4 packets. We have stopped here last week. What do we need to do this? There are competing solutions. I'll mention some of them, but the easiest to understand and the one that is deployed on our network in Switzerland is called 6-to-4. What needs to be done? Well, first we need to have routers that are at the boundary between IPv6 and IPv4. They are called relay routers. The most difficult part in this, like in many parts of TCP/IP, is to have the right terminology, and to have the right terminology in front of documents and people who don't. So here I'll try to have the right terminology, which is the one that is typically the one in RFCs, the IETF RFCs. Those are the documents that have authority for terminology. So a relay router is a router, but it's not a router in the sense we've seen. It's not doing IPv6 to IPv6, but it does IPv6 to IPv4. In fact, it does encapsulation, so it will put an IPv6 packet, put it inside an IPv4 packet, and forward it to another relay router. Now this relay router, of course, needs to have both IPv4 and IPv6 to do its job. And it needs to manage the tunnels in 2 ways. It needs to be able to encapsulate, decapsulate, and it needs, which is easy, and it needs also to know where to send the thing. If you remember Homer's case with his 2 sites network, it was easy to do a router-to-router tunnel. Now, if we do that in general, there might be hundreds of thousands of IPv6 islands, and there may be tens of thousands of IPv4 to 6 relay routers that connect to the public IPv6 internet. So how do you know where to go? That's one of the questions that need to be solved. And hopefully automatically. You don't want to write static routing entries in those boxes here. The second thing, which is perhaps less obvious, is IPv6 address allocation. If you are here in your IPv6 island, you have only IPv6 stuff, but you don't get IPv6 service from your provider, you don't get an IPv6 address. So you need to find an IPv6 address. That's the problem we had over the wireless internet that we give to you in INF 019, in the Internet Engineering Workshop. In that room, we don't have IPv6, at least for wireless, so we need to have our own address allocation. And this is solved by having an address space which is special for cases like this. We will see how it is done. And of course, we want the tunnels to be automatic, which means what is the IPv4 destination address, for example, needs to be done automatically. There are several solutions to that. The one we'll study in detail is called 624. There is a variant of it which is practically exactly the same, which is called 6RD. The only difference between 624 and 6RD is how the addresses are allocated and which addresses are used, but the mechanisms are exactly the same. Then there are other variants done by Microsoft, Teredo, ISATAP, that I will not describe in detail, but I will mention what they are doing. Warning, as usual, terminology is perhaps the most difficult part in this, if anything is difficult. 624 is a misnomer to me. If I would call something like this, I would not call it 624. 624 gives the impression we are doing translation from IPv6 to IPv4, which we're not doing. It's really a 6 to 6 over 4. Right. This is a solution for, so thank you PowerPoint for those things, which I don't know how to remove. It's not for H6 to H4 interworking, it's really a solution for H6 to H6 over IPv4. So how does it work? Well, first let's look at how it allocates addresses. Addresses, that's always an easy topic. It's like accounting. Once you know on which box to put the things, there's not much to understand. So here the story is very simple. There is a block of addresses, 2002, which is reserved for 624. So this block 2002, because it was invented in 2002, but of course it's completely wrong. This is hexadecimal digit. It's not 2002, but we read it as 2002. So this block of 4 hexadecimal digits, in other words 16 bits, is the block that corresponds to the 624 world. That means all the set of systems that use IPv6 but are connected to the IPv6 internet by means of IPv4 and specifically use 624 for the encapsulation mechanism. So this block is reserved. The internet addresses we have, the IPv6 addresses we have in the Internet Engineering Workshop starts with 2004. So they are, that's easy to find whether you use that. Second principle, if you have an IPv4 address, N, which fits on 32 bits, you can add the 32 bits to this 16-bit prefix. You obtain a 48-bit prefix, which is the IPv6 prefix associated with this IPv4 address. Now, the only difficulty is the change of notation. For example, if we have this EPFL address, which is, for example, the IP address of a wireless base station that we use in the Internet Engineering Workshop and is connected to the rest of EPFL, if we translate this 32-bit block into hexadecimal notation, we obtain this one. And this one is the network prefix that we will use for the network that is connected in this way. So anything that starts with 2002 is a 624 IPv6 address. It is a valid IPv6 address. But we know that the bits 17 to 48 of such an address are a valid IPv4 address. And as you can imagine, that's the main trick to make the tunneling automatic. When somebody will see an IPv6 address of that kind and it wonders, how do I get there? I need to go via IPv4. How do I get via IPv4? Well, I will simply get this block to construct the IPv4 destination address. This is replacing ARP. When we had IPv4 over Ethernet, we have the question, what's the MAC address that I should use to go to this IPv4 destination address when it's on link with me? Here, we have a similar problem with different terminology, different everything, but still the problem is fundamentally the same. I have an IPv6 destination address. In order to get there, we'll need to go via IPv4. What destination IPv4 address will I use? Well, here we just decipher, decrypt the IPv6 address, and we get it automatically. So we will not do address resolution of some kind. So it's a great benefit. It's possible here because the IPv6 address space is very, very large. So we can use a lot of the bits to put useful information, which we could not do in IPv4, for example. Last, there's a special thing that we need. We need to reserve one or several addresses, typically this one, 192.88.99. In fact, the entire 24-bit block is reserved, but the only address I've ever seen used is this one, .1. That's an IPv4 address. That means IPv6. It means if you send an IPv4 packet to this address, at the end of this address, at the receiver of this packet is expected to be a 624 relay router. So you know how to reach a relay router, and we will see that in detail in a second, how those things are articulated together. So to summarize now, we have reserved two blocks of addresses, one in IPv4 and one in IPv6. And once we have that, well, the solution is easy. Let's see how this solves, for example, the address allocation space for a problem for Homer, who is on a local IPv6 network, connected to IPv4 internet. So Homer has a router that has an IPv4 address, 1234. Homer uses 624, therefore it means this router will inject, will say, I am in a domain where the prefix for that domain is 2002.1234. So here the mapping is easy from this to that. So this is the 48-bit prefix. That means the entire local IPv6 network that is behind this IPv4 address. Now, this can be a small network or a large one. There can be several subnets. We can use, since we have only 48 bits for this prefix, we can use, for example, 16 bits here for the subnet. So we can have several subnets. And then every machine will need to have a final address. For example, Homer's PC will have an address that comes from this, which is the prefix of the entire network, a subnet prefix, and then its host part, which can be allocated by any of the possible mechanisms we have seen for address allocation in IPv6. For example, stateless automatic configuration or DHCP. Whatever you do here in the Internet Engineering Workshop, we use DHCP, sometimes also stateless. And we need also to configure on the router whether there are several subnets and what are the corresponding subnets. So by simply having an IPv4 address, we have an IPv6 prefix, which is a very, very useful thing. That means whenever you have IPv4 connectivity, you belong already to the IPv6 internet. That's one of the benefits of this system. Even if you are completely isolated, not at home behind a router, you can also run this on your own host. This is what Bart is doing here. Bart doesn't have a complete network, but a single device that has 624 enabled. Well, similarly, this one will get an IPv6 address made by concatenating its IPv4 address to whatever subnet you want, so typically 0, and then a host part that is allocated by whatever allocation mechanism your operating system wants to use. So in this configuration, we have been able to have IPv6 addresses, which is the first thing that is required to be able to access the IPv6 internet. Now let's talk about the relay router. There must be a relay router here from the IPv6 island. That's your ADSL modem, for example. That's under the responsibility of whoever runs this. But there must be also relay routers at the interface between IPv4 and IPv6. this is a responsibility of your internet service provider. So here, Switch has such relay routers deployed in Switzerland. So the relay router has an IPv4 address, which is whatever its IPv4 address is, but in addition, it has a different, or more precisely, it injects into IPv4 routing this address, which means that anybody who in the IPv4 internet sends a packet to this address will go to interface number 3 if this is the single router in the world doing it. Probably there are more than one router doing that. It will therefore go to the nearest of those routers that have advertised this address into the routing protocol of the IPv4 internet. Similarly, B will advertise in the IPv6 internet the block 2002.16, which means all the guys that run 624 that are behind me. So those relay routers, those 624 relay routers, have the job of advertising this address, which means IPv6 seen from the IPv4 world, and the 2002, which means IPv6 over IPv4 seen from the IPv6 world. So they will do this. Now, let's study how it will work in one case where Homer at H1, so here, sends a packet to H3, to Lisa here. Then let's look at the steps. H3 has this destination address. Right. How does Homer know to send a packet to H3, to this destination address? Well, with the classical mechanisms, DNS. So you will need, hopefully in this infrastructure, a DNS server, or you have access via those mechanisms to a DNS server that knows the IPv6 addresses. But it can be an IPv4 DNS server. Remember that a DNS server can be reached via IPv4 for IPv6 records and vice versa. So here we don't enter in the details, but you need, as usual in any network, to have a DNS server to give you this. So Homer knows this address, and Homer now is an IPv6 host with a special address, like you did in the Internet Engineering Workshop wireless network. You didn't know you were on that special thing. You were on the IPv6 internet. So what will happen? This guy sends a packet. Destination address is this. Now, this destination address, well, we use the classical IP packet forwarding algorithm. It will decide that it is not on link. Not on link because, well, we look at the configuration here. The prefix is perhaps, depending on the net mask, but classically here, 64 bits for this guy. So the destination is not on link. I will need to send it. Hopefully, I have a default route or a next hop router, which very likely in a small network like this will be router A, an IPv6 default route, which will be router A. Now, the packet will reach A because it's not destined to a local, to another guy in the same network. If you would ping another guy, then it will follow normal IPv6 routing in this cloud. Now it reaches A. What does A do? Now, A is a 624 router. So first, it realizes that it is a 624 packet, and it knows it is a 624 router. It analyzes the destination address. Now, it will look whether it is available on one of the IPv6 native interfaces here, but it is not, because the subnet mask and the routing table will say no. Therefore, it needs to send it to the default route. What is the default route? Well, the default route is this one. So any 624 router has a default route, which is this. What is this? Is the same as that. So this is this IPv4 address, which means the IPv4 address of the IPv6 internet, which we put into the 624 address. So this is just the hexa of this decimal notation. So this is a completely static configuration. Any 624 software has this hardwired. You don't need to configure it. What's the effect of this? Well, the effect is no, it has to send it on this interface, which is a tunneled interface. and it knows immediately what is the IPv4 destination address to put in the IPv4 packet, which is this one. So the packet will now come here via the IPv4 internet and will go to the nearest of the machines that respond to this address. Here it's B. It will reach B. Now, when B receives anything on this address, it knows it is the end of a tunnel. It decapsulates it and reads what's inside. What is inside is an IPv6 packet. B has now an IPv6 packet, which is the packet with destination address, this one. So B will do the job as usual, look at its routing table. Now B is on the IPv6 internet, and so is H3. So routing at B will take care of sending it to the correct next hop until it reaches H3. Voila, this is how all the things will fit together. Now it's time to wake up. I realize I have a wrong version of the slides. This is 2 here, and this is 2 here. Change it. Let's look at your solutions. I close the poll. And of course, the majority is right. The correct answer is 3. It is the IPv6 address of H1. In other terms, when we do 624, we have normal IPv6 connectivity. It's just the things are a bit weird, but the weird things are not visible here. So here, this guy belongs to the IPv6 internet. Just the router here that has, instead of an Ethernet link, it has an IPv4 link to the rest of the IPv6 internet. And in particular, one of the basic rules of IP is when you look at the IP source address, it's always the source address of the original sender of the packet, not of any router on the path. Let's continue. Lisa now responds. How will the response find its way? Five more seconds. And the answer is obviously 2. Nothing special. In fact, the IPv6 host like H3 They don't care. They just see a special 2002 address, but this is a regular, although reserved, but still is a regular public IPv6 address. So for them, it's business as usual, except now we said B had to inject into IPv6 routing the prefix 2002/16. Of course, there will be many like B's doing that, so we'll go to the nearest. One more. Now Bart. Bart is here, right? If you don't know the Simpsons characters, this is Bart. So he's alone on the IPv4 internet. What is when you're here in the Internet Engineering Workshop, you have DHCP and all the like, so you benefit from the infrastructure to do the configuration. Now, if you take your Mac or PC and do it on the IPv4 internet, what do you think should be the default configuration for the default gateway at H2, the IPv6 default gateway? I close in 5 seconds. Good, of course, there is no DHCP. There could be Slack. You could do automatic configuration, but if you do automatic configuration when you're alone, what will happen? You start an IPv6 machine that is alone. It has only IPv4 around, so it's surrounded by hostile IPv4 stuff, and it tries to acquire its address automatically. What will happen? Will it work? Will it acquire an address? Yes, but which will be the prefix? It will be link local only. It will acquire only a link local IPv6 address with no globally routable prefix, because there is nothing around to answer to the question. Typically, it's the router or a DHCP server that will give you the prefix. If there is nothing around, it will not get it. So obviously, that would not work here. What do we get, for example, in Windows? This is what we get in Windows 7. The default gateway is, in fact, an IPv6 address that is 192.88.99.1 for the prefix part. For the host part, you can give anything. It doesn't matter. So Windows repeats the same prefix as the host part. It doesn't matter, because what will happen is when a packet is sent to the default gateway, it will go to the nearest 624 router, just because of this. It will be tunneled to this IPv4 address, and then the resulting packet will be sent here. Now, the destination address will be in the original IPv6 packet, not in this address here. Allez, one more. Here is a typical configuration for Macintosh and Windows for the an IPv6, a 624 host that's alone. It has this default gateway that I said, and ETH12 is, for example, the tunnel interface. And it has another weird thing which says destination 2002/16 is on link. So this being said, what will happen to the packet from Bart here to Homer here? 5 seconds and I close. Here, well, via B and back, well, imagine, so you're the host here. You have a packet with destination address, this one. You go to the routing table, you analyze the destination address. Does it match this? Yes, it does. It matches the first entry, which says it's on link. On link means normally on the same Ethernet or wireless link. But here it's a virtual interface. This interface is on IPv4. So on link means it's on the same IPv4 network. So it means you can reach it by putting it in an IPv4 packet, which makes sense because both are 624 addresses, which means they're connected by the intermediate of IPv4. So I will use this. Now, what do I do when I have to send a packet to a destination that's on link? I do ARP and find the MAC address, but here it's not the MAC address, it's the IPv4 address. And we have seen that I don't need to find the IPv4 address. I need to find the IPv4 address that will help me to get there. So it's the IPv4 address of this guy. How do I get it? Fortunately, it is in the address. Right? The address of Homer is 1234. So I simply extract bits 17 to 48 of the destination address, and then I send it over this logical, this tunneled interface with IPv4 destination address equal to this. So the packet will go directly from here to here without going there. Of course, it would work if you let it go there, but that's a bit stupid to encapsulate twice if we can go only once. So the correct answer will be directly over IPv4 to A, then H1. Which is a bit smarter than you had thought. So if we put all things together, this is what we get, for example, on a typical Windows configuration, where we'll find that over this tunnel interface, we have a given IPv6 address. That's what we do when we connect to the Internet Engineering Workshop. We will get an IPv6 address which is derived from an IPv4 address. Of course, we have an IPv4 address. We can, if we have a printer that works only on IPv4, we can still use it if our software allows it. And I have a default gateway, which in this case is simply the, in that case, is like Bart, is the remote destination of the nearest 624 relay router. So this is not the configuration we have in the Internet Engineering Workshop. It's the configuration I have if I connect directly to the EPFL network over IPv4 using 624. You can test whether you're in an environment where 624 works by trying to reach this destination address, 192.88.99.1. If we do it from EPFL, for example, we see we're 2 milliseconds away from it, which means there is somewhere on the EPFL campus a switch router that is a 624 relay router. If I do it from home, I find that the nearest one is probably in Germany and is 160 milliseconds away from me. So if I access 624, if I access the IPv6 internet from home with only IPv4, the nearest 624 router, because of the provider I'm using here, which is Sunrise at that time, doesn't care about providing a 624 service. It's just a cheap provider. Then they rely on someone else doing it for them. Which of course is not a good way to do. If you're a decent operator and you care about providing IPv6 service, you don't want to rely on someone else's router. So you do like Switch, you deploy your own 624 routers. Now some people have criticized this way of operation, in particular the operator called Free, who's one of the, at least in the Western world, one of the operators with the largest installed base of IPv6 connectivity, where they don't like the idea that things will go to the nearest 624 router. In the direction from here to here, it's not a problem. Probably the nearest 624 router, if you're served by free, will be a free router, because this is how internet routing works. Typically, all the destinations in the same administrative domain are closer than all the others that are not in the same administrative domain. But in the reverse direction, it's more embarrassing. In the reverse direction, the traffic, where most of the traffic goes, in fact, most often we download, then we upload. So when traffic comes from a server, it will go to the nearest 624 relay router, which is very unlikely to be the free router. It's going to be a 624 router. If you go to a Californian website, it's a 624 Californian router, right? And then it will go via IPv4 to this place here. Now, some operators don't like that. They want to control, because why don't they like that? Because they have no performance guarantee on how good those 624 relay routers. So if you care and you want to give possibility for people to access YouTube over IPv6, for example, then you want very high performance routers. If you rely on someone else's 624 router, you cannot be sure. So this problem is solved by changing, by taking everything, like I said, of 624, but changing the addresses. Instead of having two well-defined blocks of addresses, the 2002 and the 192.88.99, instead of having those two well-defined reserve blocks, what is proposed, and is actually the standard today, is to do the same, but those blocks belong to blocks that are allocated to given ISPs, Internet Service Providers. So Free has its own 2002 block and its own 192.88.99, and Swisscom, if they support 6RD one day, will have to have their own, etc. So that everybody has to manage their own machines and will be sure that traffic will go to the machines owned by those operators. Other than that, it's exactly the same. So it's only the address that change. 624 is officially replaced by 6RD, but is still in the field. As we can see, Switch provides 624. Voila, so this is perhaps the most important transition mechanism for going from IPv4 to IPv6, because we have seen it solves all the problems. In fact, when you go to the Internet Engineering Workshop and use IPv6, you don't realize you are using a transition mechanism. So this gives access to the IPv6 Internet to parts of the world that have only IPv4, and it solves all the problems. There's no special configuration of any kind, provided the 624 relay routers that you use are properly engineered and are good performance. There is a number of other bells and whistles that we will not discuss. If you use just 624, like I said today, you have a problem. If you do it from home, you're probably behind a NAT. Now, 624, as I said, doesn't work natively behind the NAT. So you need to configure the NAT to be able to operate in this way. There is which you can do. This is what providers like Free do. They do it because typically if you're a customer of Swisscom or Free, the NAT box is controlled and configured by Swisscom. So they can, if they give you a 624 or a 6RD service, they can also configure it. Now if you use a cheap provider like Sunrise that lets you buy your NAT at Migros and hope you can find on their website how to configure it for operation, then that's a trouble. This trouble has been solved by Teredo. Teredo is a variant of 624 invented by Microsoft, believe it or not, that uses is very similar to 624, but of course the addresses are different. The block reserved for Teredo is this one, 2001. It was invented 1 year before 624. It was finalized 1 year before 624. It's a 32-bit block. And the rest is very much the same. You have all the same concept of relay routers. But the tunnels are a bit different. The tunnels are inside UDP. This is because of NAT and firewall problems. and a number of details that I will skip. Teredo in principle works. It's called Miredo in Linux and Macintosh. But if you see, for example, if I try to ping from home, which is 7 kilometers away from this server, if I try to ping this server using Teredo, I find response time of 164 milliseconds, which means I go probably a very long way. And if we analyze this, we find that we go via Germany. So we go via a relay router that's in Germany. So it works, but only nominally in some cases. You need active support of your provider to put in place the relay routers. And if you do that, probably you're more likely to use 6RD than 6 to 4. Voilà. In summary, 6 to 6 over 4, which is called 6 to 4, solves the problem, and everything is automatic, as we have said. In particular, the relay routers are stateless. They do their job as relay routers. A bit weird, they have this encapsulation, decapsulation, but in the figures we've seen before in the animations, there was no information at a relay router that Bart or Homer were doing something special. Voilà, that's the end of the 6 to 4 story. We do a break and we see the 4 to 6 after the break.